Welcome. In this class, we'd look at the application of the momentum balance equation that we derived. What I'm going to do is, I'm going to show you or I'm going to apply the equation of motion to the same situation that we considered earlier. The case of a thin film of liquid falling over an inclined plane, a Bostwick-Hughes commutator case. And you'll be able to see how simple it is to arrive at the final relationships of use when we use this equation compared to when we did shell balances, okay, compared to the shell balances. Shell balances took a long time and so on and so forth. Now, we spent enough time and effort to set these equations of motion that we can directly use in appropriate situations. Okay, so we might as well use that. You just need to have it by your side. You could refer to that. I will not expect you to remember any of those equations. Don't worry about it. Normally, those are very long equations, very complex terms there, different subscripts and so on and so forth. I will not expect you to remember it. You could just take those equations there and directly start using them. Okay, so that's the reason I asked you to make a copy of those equations and keep it aside. So, some applications of the equation of motion, first to the same situation, the steady state falling film case. So, the geometry here is the rectangular Cartesian coordinates geometry, right? That is quite easy to see. So, let us use equation C1 of table 3.4-1 to get the shear stress profile. Okay, what is equation 3.4-1? I think I'll need to open up that equation again. Okay. So, this is the rectangular Cartesian coordinate system for the equation of motion. So, this is the x direction, y direction, z direction. I think we are looking at the z direction here. We had written it for a z direction. So, this can be taken for, okay, we are looking at the first equation here, C1 to begin with. This is a general equation. Okay. The second ones are for Newtonian fluid with constant rho and mu. Here, this is a general equation. Let us consider this equation. Okay. So, this if we take and apply it here, it's quite easy to see that there is no bulk velocity in the x direction, there is no bulk velocity in the y direction of the film. This is the z direction, the bulk velocity is only in the z direction. Therefore, only Vz is relevant, and the equation that contains Vz is C1, and that's the reason why we went with C1. When we take the C1 and cancel the terms, I'll show you one by one. Then we get something like this. This is a steady state analysis, as we said. Therefore, there is no variation with time. The first term goes to 0. There is no Vx, right? There is no velocity in this direction. Therefore, that is 0. There is no Vy, so that goes to 0. There is certainly a Vz. However, we have taken the case of well-developed flow, which means the Vz is not varying with z. Therefore, Vz is not a function of z, and therefore, this derivative goes to 0. And we have already chosen that the pressure does not vary with the length, and therefore, dP dz is 0 by the chosen condition. This term remains. Tau yx is not a function of y, therefore that goes to 0. Tau zz is not a function of z, therefore that term goes to 0. Okay. Plus rho gz remains. See here, do I have the details here? For getting an idea of why it's not a function of y, tau yz is not a function of y, you could resort to the direction of motion and the direction of action, simplistically speaking. We have already seen that two different shear stresses could contribute, two different shear rates could contribute to a shear stress, and so on and so forth. So, to get an idea here, this is the shear stress that arises in the y direction because of the motion in the z direction. Okay, there is motion in the z direction, there is no shear stress in this direction. So that's the reason why this is 0, it's not a function of y. And there is no shear stress that is going to result in this direction because of the motion in this direction. That's the reason why this normal stress is 0. There is no variation in velocity and so on and so forth. So that is 0. Okay. So what we get from this equation is, I think I need to get back to this. Gz is nothing but g cos beta. Okay, g was in this direction, this was the beta, so the component here is g cos beta. And if we substitute here, we are going to get 0 on the left hand side. This term remains dou x of tau x z minus, plus this becomes rho times g cos beta, okay, which is exactly the same equation that we had earlier. Okay. So just by using this equation, cancelling out the relevant terms, we could directly get this equation. Okay. We don't have to go through a significant amount of effort which we need to expend if we do shell balances. Now, let us try to get a velocity profile in this Newtonian fluid. It's water flowing, as we said. Water is a Newtonian fluid. And for this, we can use the next equation, C2, in table 3.4-1. I'm going to write the equation, so I'm not going to go back and show you that equation. Please look at the table that you have made a copy of and find out that equation. Yeah, that would be an easier way to do. Initially, I need to make this connection, and then once you have already made the connection, you can directly refer to the equation. This would have been the equation C2 in table 3.4-1. When we cancel the terms, the first term is the process is at steady state, therefore there is no variation with time, the first term goes to 0. We've already seen there is no Vx, there is no Vy, therefore these two terms go to 0. We've also said that Vz is not a function of z, well developed flow, and therefore that is 0. We also said that pressure is not a function of length. The fluid is very thin. We went through a long argument to establish this earlier. You can go back and look at that argument. Plus dou squared Vz dou x squared. This term of course remains. There is a variation of Vz with x. There is no variation of Vz with y. It's all the same at various y's. And similarly, there is no variation of Vz with z, well developed flow. Okay. So these two terms go to 0. These are quite straightforward to see. Plus rho gz. Now, the only terms that remain, 0 on this side, mu dou squared Vz by dou x squared on this side, plus, of course, we've already seen that gz is g cos beta, therefore rho g cos beta. And this 3.4-3.4.1-2 was exactly the same expression, or you could write this as, to see that it is the same. You could write this as, I'm taking one to the other side and so on and so forth, or let us say that I've taken rho g cos beta to the other side. Therefore, you could write this as mu dou x of dou Vz dou x, this is second order derivative, dou x of dou Vz dou x, equals minus rho g cos beta, and which can be written as dou Vx dou z, if you solve this equation once, minus rho g cos beta by mu times x. Okay. And this was exactly the same equation as what we got earlier. Okay. So, by applying the equation of motion, we significantly simplify the effort that we need to put in to arrive at relevant insights. Okay. This is a reasonably short lecture. I think I've shown you one application. I think I'll let it sink in. And when we come back in the next class, we'll look at other applications. all of relevance, all of heavy relevance to whatever is being used in the body, in the industry, in various biological systems. See you then.